First of all, let me thank Professor Manjil Saikia for the invitation. And today I'm going to speak about how mathematics has helped shape civilization. Um, so, mathematics, how did it start and how did we start to count? Humans, we did not evolve with any compulsion to count. So even now there are societies, tribal societies where only up to 3 or 4 people count because it suffices for their basic needs. So from an evolutionary perspective, we did not need to count so much. But eventually we did, and after numbers and arithmetic was invented, it paved the way for living in large independent society because we could trade, we could tax, and we could lend with the help of numbers. And I believe that the impetus that numbers and accounting and arithmetic gave was quite large to the evolution of societal living. People tend to give more credit to agriculture, animal husbandry, and things like that. But I believe that mathematics also had a tremendous influence on this evolution of living in large independent societies. So in fact, the earliest known piece of mathematics or arithmetic was an accounting table, and it was a Babylonian clay tablet, which I'll show in the next slide. But the first recorded counting is even older, at 20,000 years, and maybe even older. So humans, they made tally marks on bones or pieces of wood to keep account. So for example, here on the left is a picture of a bone fragment where you can see marks made by Neanderthals, who were our close cousins. They became extinct about 40,000 years ago. And on the right, you can see a Babylonian clay tablet where it's written in cuneiform, and you can see these markings are sort of like accounting. So what next after counting? We started to count with our fingers. So even with an absence of language, we could trade because you could just point things with your finger, and you could point like 2 for 2 fingers for 2 and 3 fingers for 3 and so on. And these accounting practices, they help sustain businesses because without accounting, without knowing whom you had to tax or whom you had to lend or from whom you had to get the profit, you would not be able to sustain a business. And this, so only with positive numbers you could not do business because you naturally needed fractions, like you had to divide your profit among your partners. For example, if there are 3 people in the family who are doing the business and you have to divide by 3, so 1/3 you needed to know about the fraction 1/3 and so on. So this naturally fractions were introduced for dividing things such as crops, land, or profit and so on. But this concept of negativeness was not very easy to imagine. So it was a major leap forward in our evolutionary thinking. And it was started by Indian and Chinese accountants to represent deaths around 300 BC to 50 AD. In fact, Brahmagupta in 628 AD, he gave the rule that a negative number times a negative number is a positive number, which we are very familiar with. But in the West, this tradition of negativeness or this concept of negativeness was very slow to pick up because they were more focused on Greek mathematics, which was done mostly with symbols than with numerals. And this first step towards negativeness was implemented by Fibonacci in his famous book Liber Abaci, which is a book of calculation. Basically, it deals with algebra and arithmetic. And you might know Fibonacci from his more famous Fibonacci sequences than from this book. In fact, in this book itself, the Fibonacci sequences arise as a counting problem for mating of rabbits. So on the left is a picture of Brahmagupta, and you can see calculations behind him. And on the right is a page from Fibonacci's book, Liber Abaci. So after Fibonacci, so from Fibonacci's book, the Europeans, they came to know about a series of simultaneous linear equations whose solutions could be negative number. Earlier, if there were negative numbers as solutions, then they tend to ignore and say that this solution was not possible or something like that. But things moved very slowly after Fibonacci, and in fact, Blaise Pascal, who is a famous physicist from the 17th century, was still reluctant to accept negative numbers. John Wallis, he made this concept of negative numbers into a pictorial concept in his book, A Treatise of Algebra, where he helped visualize these numbers by the concept of a number line. And in physics, negative numbers is so much of calculations that they became imperative for the development of physics. and so on. So we see that it took almost all of human history to reach negative numbers, but the rest of the 350 or 340 years from negative numbers have had tremendous progress compared to the last 30,000 or 40,000 years of arithmetic or counting. And mathematics had a big role in this development of the last 300 years. So here is a picture of Wallis's book, where you can see the concept of a number line. Instead of numbers, he gave symbols, but this is the number line that we are more familiar with. So what about zero? We Indians are very peculiar about the number zero, because zero was used as a number first in India. So zero as a placeholder was already known before Indian mathematics. In fact, in the Babylonian clay tablets, you could see zero used as a placeholder for certain cases. And the generally accepted oldest symbol for zero as a placeholder was in the Paksali manuscript, which is now at the Bodleian Library in the University of Oxford. And this has been dated between 224 and 383 AD. The dating is a there has been some dispute, and I don't want to go into this here, but if you have any questions, then I'd be happy to answer. But as a place in the number line, it was again Brahmagupta who gave zero as a number in itself, and he gave propositions such as anything added to zero gives back the number itself, or anything multiplied by zero gives you zero, and so on. Again, the West was a bit slow to get the concept of zero as a number, and it came via Al-Khwarizmi, via his book called Al-Muqabla, Algebra Al-Muqabla in 830 AD. And he gave this as a tool to use in algebra. But again, like the negative numbers, the concept of zero was not accepted immediately. The acceptance was gradual, and the earliest official use was only in the 12th century in Pisa, again for keeping, sorry, not in the 12th, 14th century, again in Pisa, for keeping accounts. So, but from this event, the acceptance of zero, and then subsequently the acceptance of negative numbers, Western civilization, it accelerated at a great pace compared to the last 300,000 years of human history. And from this acceptance of zero and negative numbers, the concept of double entry bookkeeping, which revolutionized how business was done, came into being, especially in places in Italy, which were seaports, because these were important trading links between the East and the West. So merchants from East used to meet in the seaports, and merchants from West used to meet in the seaports to do trading between both these two hemispheres. So here is a Russian stamp depicting Al-Khwarizmi. Al-Khwarizmi's name gives the word algorithm, and his book Algebra Al-Muqabla gives the word algebra. So he is a very important figure in the history of mathematics, especially in Islamic science. Let us come to some certain tangible concepts now, tangible topics in mathematics. So let me start with geometry. So far, we have only discussed arithmetic and accounting as having helped civilization. But what about geometry, which is one of the subjects that we study in school? And the geometry had a tremendous influence in Renaissance, when there was this explosion of art, architecture, science in Italy and all over Western Europe. Geometry and algebra and mathematics were really at the forefront of these developments. So to delve more into this, let's look at triangles. Okay, so geometry is very useful in making maps, in architecture, in art, and so on. And the basic idea of geometry lies in the properties of triangles. So you would probably know about Pythagoras' theorem, which states that the square on the sides of the right angle triangle is equal to the square on the hypotenuse. And from there, Pythagoras also, the school of Pythagoras also found the concept of irrational numbers, because if you have a square of side length 1, then the diagonal would be of length square root of 2, which is an irrational number. So geometry was essential for the construction of things like Egyptian pyramids, because there you had to know the concept of volume of a prism. Also in more recent times, Mughal gardens, the Charbagh feature of Mughal gardens, where you really needed to know proper calculations and proper mensuration of parameters and things like that. Okay. So here is an example of the use of geometry. So this is a famous building in Florence called the Baptistery in Florence. And before the Italian Renaissance, if you look at paintings, I'll show you a picture later on. If you look at paintings, the proportions were not really how it should be. So the pictures were really out of proportion. And this was because the concept of projection was not available to artists. And the concept of proportions only started after the Italian Renaissance, where artists like Brunelleschi figured out how to draw pictures using projections. For example, here you can see the projections of the lines, which are basically projections of the baptistry on a two-dimensional surface. So this three-dimensional picture has been projected onto a two-dimensional surface, and this was an important advance in art and architecture, and it all started with the work of Brunelleschi in Florence. Florence was a hub of actually mathematics science. For example, Galileo was a Florentine, and even architecture and even literature, because one of the greatest Italian writers, Dante, was also, I think, lived in Florence and worked there. Anyway, so let's come back to geometry. And one important figure in geometry is Thales. So Thales went to Egypt and he started to absorb the results of teachings of the Egyptian mathematicians and added to this knowledge his own results. For instance, he proved that isosceles triangle had two equal angles, and that to know a triangle, it is important to know only one side and two angles. And this has a very important consequence, because sailors could use this property of the similarity of triangles, or of the property that to know a triangle you only needed to know one side and two angles, to find the distance from the shore of the ship, because you already know the length of your ship, and then you can calculate the angles that the two ends of the ship makes with a point in the shore, and then using that you can figure out the length of the sides, or the height of the triangle, and so on. Okay. So heights of pyramids and other structures could also be found using such concepts of shadows and similarity of triangles. So it was really an important result that Thales gave. And this is a bust of Thales. So let's again look at some other results of triangle geometry. So creating right angle triangles is a cornerstone of the construction industry, because using the concept of right angle triangle, you can make a lot of different things. For example, there is a very important result that we read in high school geometry, which is that the angle in a semicircle is a right angle, and as well as Pythagoras' result. So to make right angle triangles, it was really important to use this sort of results. Another pivotal figure in geometry and in mathematics is Eratosthenes, who used this knowledge to calculate the circumference of the earth. So how did he do this? So here is a picture of Eratosthenes. If you look at the right hand side, if you look at the right picture, you can see that there are two places marked. One is Alexandria and one is Syene. Eratosthenes was the chief librarian of the Library of Alexandria, and he knew that on summer solstice, the rays of the sun, it falls straight in the Tropic of Cancer. So he fixed a place in the Tropic of Cancer, which is Syene, and you can see that the rays of the sun are falling straight in a 90-degree angle at Syene. And he then calculated the angle that the rays of the sun made at Alexandria, which is the angle alpha here. And then he calculated the length, the distance between Alexandria and Syene, which is L here. And then he used the idea that the whole circumference has 360 degrees. So for the sun to make an angle of alpha, you needed the length L. So then you can use the unitary method to find out how much length should be there, so that the whole angle is 360 degrees. And Eratosthenes' calculation was remarkably accurate for his time. So after geometry, a natural extension is of trigonometry. And in trigonometry, we study angles and ratios, which are quite useful for navigators who use sine and cosine tables to carry courses and carry tools such as quadrants. And making maps was an important skill then, because then only way of communicating between two places was to really go there and communicate, or to send a letter, or to send somebody with your message. And for that person or for that letter to reach that place, you really needed to know where that place exists in the map. So mapmaking was very useful, was a very useful tool. Even now, it is a very useful tool. For example, modern day GPS, it uses a lot of geometry because you have to track the movement of the satellite, its orbit, rotation of the Earth, axis of the Earth, and so on and so forth. So it needs a vast amount of calculation, and it needs to be updated very frequently so that it can give accurate information for us. So just with the flip of the mobile, we can now get the correct position that we are in now. And all of this is because of geometry. So as I said, mapmaking was very important. And for that, geometrical projections was quite important. And one of the most famous projections that we know is the Mercator projection. So on the right is the Mercator projection that we are very familiar with. So this is how the world map looks like. But there is a problem with this projection, because this projection only keeps the distance between two places invariant. That means the distance between two places are correct, but the angles, they are mismatched. So Greenland is shown in a really obscure shape, whereas Greenland is quite small compared to how it looks here. And Africa is much larger than how it looks here. Similarly, Australia is shown as a bit larger than what it is, and so on. And Antarctica is really not this large. So you can see that Antarctica is completely in the bottom, but it's not so large. So there is a problem with this, and this is because of a very interesting result called Gauss-Bonnet theorem. And I can go into it in more details if you want in the session. And on the left is a globe, and this is the earliest extant globe that exists, and it's in Nuremberg. It's a city in Germany, and this globe is displayed in the museum in Nuremberg, and it's quite a fascinating object. So if you get a chance to go to Nuremberg, I would recommend that you look at this globe, and you can figure out where is Assam and where is India and so on. But there are some places which are missing from this globe, because at the time it was not known that these places existed. So I have been focusing on art and architecture for the last few minutes, and really geometry is very important in art and architecture, because calculation of volumes, of cylinders, domes, etc. was very useful. And for that, you needed to know accurate approximate values of pi, which is really a geometric constant, because it is the ratio between the circumference and the diameter of a circle. So other advances in art resulted by advances in perspective, projection, and optics, as I told you about Brunellesi's portrait of the baptistry before. And this art was completely revolutionized by the ability to make accurate lifelike paintings. Nowadays, this is still used, but architects nowadays use computers to do all of this mathematics. In fact, visual art effects artists or designers for video games, they also use computers to do a lot of mathematics. But all of this is hidden in the software that they use, so we don't really see the mathematics come out. So, for example, here is a very bad two-dimensional portrait of a three-dimensional object. So you can see there are some people standing between two towers, and the proportions are completely off. So the tower, the window of the tower is so small, and there is this person who is standing, and that person is as tall as the tower. So it's completely impossible that this is really how it looks like, because there was no concept of perspective in painting. So people were not really able to draw accurate lifelike images. And on the left, you can see the dome of Hagia Sophia, which is an important architectural marvel in Istanbul. And you can see that the dome is really perfect. To make the dome, it required really precise calculations of the volume of a cone, the area of a cone, and approximate values of pi. So, and this is about 800 years old. So really a lot of mathematics went into making these kind of buildings, which is now possible just using the computer. So let's come to another topic, which is algebra. And we are very familiar with algebra because we are used to doing algebra in school mathematics, where our algebra is more like using symbols, but actually most of high school algebra can be done just using geometry. For example, to solve the quadratic equation x squared plus bx equal to a, you just need to complete the squares. And completing the squares is purely a geometric way of solving quadratic equations. So this move from geometry, because if you look at Euclid's book, so Euclid's famous book Elements, this is not only geometry, it contains a lot of different things. So there also you'll find a little bit of algebra, but this algebra is disguised as geometry. So you would not really see the pictures and realize that this is algebra. So this move from geometry to symbols was done in the 16th century via Francois Viete. And nowadays, every practical thing that we do really uses a lot of equations in the background. So here is a problem from Lilavati, and you will see that this is an algebraic problem which is given as a word problem. So looking at this in the first glance, you might not think that this is an algebra problem, but if you read it properly and you try to assimilate what is being asked, then you can formulate this as an algebra problem, as a problem of a solution of a system of linear equations, and so on. So learning to think in abstract terms, like in symbols, and to handle abstract objects was an important cognitive tool in the development of human cognition. And different degree 2 equations where you could really visualize this sort of equations. For example, ellipses could be orbits of planets, parabolas could be the trajectory of a throw of a stone, and so on. Okay. So algebra is very essential in looking at various physical phenomena. And in fact, it is extensively used in all of physics. For example, in Newton's Principia, you will see a lot of algebra being used. And knowledge of solutions of higher degree equations is quite essential to make curvy objects. For example, cars. To make cars, you really need to solve a lot of difficult equations to find that curvy shapes so that the aerodynamics of the car is good and it's safe. So the automobile industry really uses a tremendous amount of algebra. A branch of algebra, which is abstract algebra, is quite modern in the sense that it started from the work of Galois, but abstract algebra has a lot of applications. For example, in physics, to make predictions of elementary particles and to give an understanding of how our universe looks like, uses some results of Emmy Noether, who was a famous algebraist of the last century. And there are other applications of algebra, such as Google search, Nash equilibrium, and so on. Okay. So here is a picture of Everest Galois, and here is a picture of Emmy Noether. Apart from algebra and geometry, what are the other applications or other developments in mathematics? So for example, we have logarithms, which is an offshoot of trying to help astronomers to do their work, because logarithms transform products into sums, which make it easier to calculate. And slide rules, which is an offshoot of logarithms, have been in use until the last century. So it was used in the Manhattan Project, for example, in Fermi's calculation of a controlled nuclear fission experiment, or in the Apollo missions to send people to the moon. We used a lot of slide rules and logarithms. Other developments which I did not touch at all, such as imaginary numbers, solutions of equations, quantum mechanics, quaternions, and so on, have had a lot of applications in physics, in industry, and so on. For example, in the music industry, one uses mathematics. So if you know about the Yamaha synthesizer, then you can read about it. So how the synthesizer uses mathematics. Okay. And there are even more developments, which again, I did not have time to touch upon, but I can answer questions in the session. So for example, calculus, it opened up a whole new world. And everything that we do now probably uses calculus. Every aspect of life probably uses calculus. Information theory, which is the basis of all modern day communications, the way that I'm communicating via video, it uses a lot of mathematics. Statistics is used in almost all branches of study. Whatever you study, you are going to use statistics, and much more. So mathematics really has helped shape our civilization in ways that we may not be aware of, but it's always there in the background. So this is what I wanted to say. And in the interactive session, I'd be very happy to answer more questions and also talk to you about some of these aspects, and also about some of the books that you can read of all of these things. So thank you so much. And I hope to meet you in the interactive session.